Hello my dear students, you are most welcome to my class. Myself Dr. Apil. As you know, we have started new lecture series on group theory, and in the last class we have discussed some basic properties on group theory like operations and some important properties on operations like culture property, associative property, existence of identity, existence of inverse, commutative property, and also we have discussed some algebraic structure, okay, like group wide, semigroup, and also some numerical problems we have discussed in the last class. And if you have any doubt on that class, then you can message or comment on the comment box, then I will try to explain in the next class. Okay, so my dear student, today also we will try to discuss some important algebraic structure. Before I am going to that algebraic structure, just I will try to do a quick revision on basic concept which already we have discussed in the last class. So you see here, if we consider an operation, suppose star, okay, and a non-empty set, suppose S is a non-empty set, and together with a operation star. So this is a structure, and this type of structure we call here algebraic structure. Okay, this type of structure is called here algebraic structure. Okay, now if this set S is nothing closed with respect to this operation, right? You see here, if this set S is closed with respect to this operation star, then this star is called binary operation. Set S is closed with respect to this operation, then the operation is called binary operation. And you see, suppose if this set S is closed with respect to binary operation this star, then this S is called group wide. Under the operation this star, okay, then we call this S is nothing group wide under the operation this star. For example, suppose if we consider the set of natural number and operation is plus, then you see here this n set is nothing closed with respect to this operation plus, and that's why we can say this plus is nothing, this is a binary operation on the set capital N or set of natural number. And as well as we can say this n is nothing, this is a group wide with respect to plus. But you see here, in case of this one n and minus, you see here this minus operation or subtraction, this operation is not binary on the set n, because you see the set of natural number n is not closed with respect to subtraction. Because you see here, suppose if we consider any two elements, suppose 1 and 3 from the set of natural number, and if you subtract them, then we get here minus of 2. But you see here, this minus 2 is not a natural number, that means this minus 2 is not in n. That means what we can say, this minus operation or subtraction is not a binary operation on the set of natural number, and hence we can say this set n is not a group wide with respect to discuss another important structure in the last class, which is called semigroup. Now what is semigroup? Again here you see, if we consider a non-empty set S together with a binary operation, if we consider this star is nothing, this is a binary operation, then this set S is called semigroup with respect to a star if it is satisfied one condition. And what is that condition? If we satisfy associative property, yes, associative property. That means this property, A star of B star of C is nothing, A star of B star of C for all A, B and C belongs to S, right? You see here, we consider a non-empty set together with a binary operation and it is satisfied this associative property, then we call this as is nothing, this is semigroup. This is what? semigroup. Then this S is called semigroup. Yes, and also you see here, we mention here this S is nothing, is a non-empty set equipped with a binary operation star. That means this set S satisfy the closure property here with respect to this star, as well as here this star S is satisfied this associative property. That means if this set S satisfy two properties, one is closure properties, another is associative property, then we call the set S is semigroup with respect to the operation star. Is it okay? For example, if we consider this operation, suppose this one, n multiple. You see here, this set of natural number with respect to multiple will be a semigroup, because you see this set n, set of natural number, is close with respect to multiple. That means this multiple is nothing, this is a binary operation. And then you see this set of natural number also will satisfy these properties, these associative properties. That means this n is nothing, it is a group or semigroup with respect to multiplication. But if we consider this operation, suppose this one, this set of integer and minus. Now you see this set of integer will be closed with respect to subtraction, because if you take the difference between any two integer number, will get or again is an integer number. That means the set of integer is this closed operation. That means this minus is nothing, this is a binary operation. But here you see the set of integer or the integer number is not satisfy the associative property. We can easily verify this thing. Yes, that means we can say the set of integer is not a semigroup with respect to subtraction. Okay, so all those things already we have discussed in the last video or last lecture, so you can go through that lecture first. Okay, so today we'll discuss another important structure. So you see here structure here, the structure is nothing, this is monoid. Now you see the definition of monoid first. You see a semigroup is called monoid if there exists an identity element. If there exists an identity element, or you can say there exists an element E in G such that this is happened. Yes, this is the property for identity element, which already we have discussed in the last class. So you see here, if we consider a semigroup structure, suppose this one G and star. Here you see G is a non-empty set and star is nothing, this is a binary operation. Then this, and suppose we consider this structure is a semigroup, then this structure is said to be a monoid if it has an identity element with respect to this star. That means this structure is said to be a monoid if it is closed, right, and then associative, and then associative, and then what? Existence of identity. Existence of identity element. Bas. If this is satisfied, then we call this structure is nothing monoid. That means if you see here, I mentioned here the group semigroup. That means this satisfy these two properties. First two properties will come from semigroup from the definition of semigroup. And then moreover, if G has some identity element with respect to this star, then we call this is nothing, this is a monoid. For example, if we consider this one, suppose Z and plus, then this structure, that means this set of Z, set of integer with respect to addition will form a monoid. How you see here? First of all, you see here this will satisfy the closure property. Why it will satisfy the closure property? Because you see, if we consider any two integer number, then their addition or their sum also will get an integer number. That means again the sum or resultant value also will be that set. Okay, that means this is closed. And also we can easily verify that the associative property will also satisfy the set of integer or integer number with respect to addition. That means the second properties also will satisfy. Now come to for third properties. That means is there exist any identity elements with respect to plus or not. And in the last class already we have discussed 0 is the identity element with respect to addition. So if we consider operation is nothing addition or plus operation, then you must remember the identity element is 0. Now check whether this 0 is in Z or not. Obviously it will contain, because you see set of integer will contain 0, because 0 is an integer number. So what we see here, set of integer is closed with respect to addition with and it is satisfy the associative property, and also it has the identity element 0. That means this is nothing, this is a monoid. What we can say, the set of integer is monoid with respect to addition. But you see, if we consider this structure, what is that structure? Suppose if we consider this one, n plus set of natural number n with respect to addition. Now is this one is a monoid? No guys. Why this is not a monoid? You see here, this set of integer this set of natural number will satisfy the closure property with respect to addition. Okay, it's okay, no problem. The first property is satisfied with respect to addition. Yes, the set of natural number is closed. And again also you see here the set of natural number or the natural number will satisfy the associative property. So second property also will satisfy here. But what about the identity? Is there exist an identity element with respect to addition? We also know that the identity element with respect to addition is 0. This identity element 0, this 0 is not belongs to the set of natural number. That means the set n does not exist any identity element with respect to addition. That means what we can say, this set of natural number is not a monoid with respect to addition, right? Similarly, there will be many structures which will be monoid. Okay, for example, suppose if we consider the set of real number and with respect to plus, yes, so if we consider set of real number with respect to plus, this is also will be an monoid. Okay, so you can just verify. And so what we see here, the set of integer with respect to multiplication will form a monoid. Again you see, you can easily verify here, set of integer with respect to multiplication, is it monoid? Yes, obviously it will be monoid, because you see set of integer will satisfy the closure property with respect to multiplication. It will satisfy the associative property with respect to multiplication, and also it contain the identity with respect to multiplication. Now what is the identity with respect to multiplication? One is the identity with respect to multiplication, guys. Already we have discussed in the last class. So one is the multiplicative identity, and also we know that one is in Z. Z contain the identity element 1 here. That means this Z satisfy all the three properties of monoid. That means this Z will form a monoid with respect to multiplication. But what about this set of natural number with respect to plus? This is not a monoid. Yes, so this is no. Now you see in an important structure we consider here, the set of all subsets, that means collection of all sets, or you can say power set with respect to union. Is this is form a monoid or not? So you see here, if we consider P is nothing, PS is nothing, this is the power set of S. That means which contain all the collection of the subsets of S, and union is then operation, binary operation. Now question is that is this one is a monoid or not, right? You see here, just I will take a numerical values of this S. Suppose if we consider S is nothing, S is our A and B, right? Now you see here, then what will be the subset of this S? One will be phi, another will be contain A and V and our AB. Bas. So this will be our P set, right? This is our P set, power set of this one. This is our P set. Now if we want to verify whether this P set or power set is closed with respect to union, whether this is closed, you see it will be closed. Why? Because you see, if we consider any two sets from here, any two elements from this power set, and if you take the union of them, you will get another set, and which will be in here. You see, if we consider these two one, here you see phi and this set A, their union will be A, will contain A only, so this set will be there. Again, if we consider any two one, suppose if we want to these two set, and if we take the union of this one, then the set or resultant set will contain A and B, that means this set will be there. So if we consider any two sets from here, then their union also will be here, so that means this power set is closed with respect to union, right? And similarly you see it will satisfy associative property, because already we know that the operation, intersection and union always satisfy the associative property, right? So it will satisfy the associative property. But what will be the identity element of this set? What will be the identity element of this set? You must remember the definition of identity element. You see here, an element E is said to be identity element if it is happen E star A equal to A for all A. For all A, if this is happened, then we call E is our identity element, right? Now you see here, so now you see our this operation is nothing union. Now if we consider this E is nothing phi, and if we consider A is any sets or any elements from here, what we get? You see here, suppose if we consider this one, then what we get? Union of B, then what we get? This will be B. Similarly, if we consider this phi union of this AB, A and B, then also we will get A and B. So if you take union of any elements from here with this phi, we get that elements. That means this phi is nothing, this is the identity element of this PS with respect to the operation union. That means what we can say, this P is nothing, this PS is nothing, this is a monoid with respect to union. That means what we can say, the power set or collection of all the subsets form a monoid with respect to union. And similarly, if we consider intersection, the operation is nothing intersection, then also we can easily verify this power set is form a monoid. That means it is satisfy the closure property, associative property, and also it will exist the identity element. Yes, so that's why we can say this is a monoid. My dear student, देखो another important structure is, so you see here an algebraic structure G and star is called group if it is satisfy some properties. You see, first of all they mention here algebraic structure, that means G is a non-empty set and this star is nothing, this is an operation, and obviously we consider here this is binary operation. Okay, so a non-empty set which is said to be a group if it is satisfy here some properties. There will be four properties. The first property is, you see here, closure property. That means for any two elements A and B belongs to G, such that A star B is belongs to G. Yes, then we call this G is nothing closed. That means closure property need to satisfy here. And then the second property is nothing here, associative property, which already we have discussed. And the third property is, you see here, which is called existence of identity. Existence of identity, right? So identity properties is this one, already we have discussed. Okay, that means this E is called identity element if for any A belongs to G, for any A belongs to G, this is happen E star A equal to A star A. If this is happen, then we call E is an identity element. The existence of identity means this type of identity element must exist in G with respect to this operation. Okay, and after that another property which is called existence of inverse. That means for any element of G there must exist an inverse element with respect to that operation in that set G. Yes, that means for each element A in G there exists an element B in G such that this is happen, A star B is equal to identity, or this one we can write like this also, B star A is equal to identity. That means for each element of G there must exist a inverse element with respect to that particular operation in that set, right? Then this set G, then the set G is called group with respect to this binary operation star, right? You see here, again I repeat here, this non-empty set G is said to be a group if it is satisfy first closure property, then associative property, existence of identity. That means there must exist some identity element, and the last property is the existence of inverse. That means for any element of Z there must exist inverse element also in G under the particular operation star. Yes, so if this property is satisfied, then we call G is nothing, this is a group. So for example, if we consider the set of integer with respect to plus, you see, set of integer with respect to plus. Now question is that is this one form a group? Yes. Why? You see here, first of all we need to show closure property, and then associativity, and then existence of identity, and then existence of inverse. So you check whether this Z is satisfied these properties or not. Obviously this Z will close with respect to addition, already we have discussed. Yes, for any, if we consider any two integer value, then their sum also will be integer, that means this is closed. And also with respect to addition, the set of integer is satisfy associative property, and also we know that the identity element also exists in G, because you see with respect to addition the identity element is 0 and 0 is in Z, right? 0 is in Z, so that's why we can say the Z exists the identity element. Now come for existence of inverse. So you see here, if we consider any elements, suppose 2 in Z, then the inverse of 2 is nothing minus of 2 with respect to addition, and also you see this minus 2 also in G. If we consider any element, any integer number from Z, suppose A, if A is an integer, then obviously minus A also will be an integer, that means minus A also will be an integer. But you see here, if the inverse of A is nothing minus A with respect to addition, right? Or you can say the inverse of minus A is equal to A. So that means what we see here, for any element of, so that means what we see here, any element of Z, there must exist inverse element in that Z with respect to this addition, right? That means this set of integer is nothing, this is formic group. And you see, similarly, if we consider suppose Z set of integer with respect to multiplication, is it formic group? Set of integer, you see, if we consider set of integer, but you must remember with respect to multiplication. Now is it group? No. Why this is not a group? You see here, this is not a group, this is not a group. Why this is not a group? You see here, this set of integer is closed with respect to multiplication. It will satisfy the associative property. It will also exist the identity element, because you see, one is the multiplicative identity and also one is in Z. Okay, so existence of identity also will hold. But what about the inverse? Now you see, what is the inverse of 2 with respect to multiplication? 1 upon 2. You see here, 1 upon 2 is in Z? No. The element 2 has no inverse in Z. Similarly, if we consider 3, what will be the inverse of 3? This is 1 upon 3 with respect to multiplication, and which is not in G. That means what we can see here, this Z is not satisfy the existence of inverse property. That means there are many elements in Z which has no inverse in Z. That means we can say the set of integer is not a group with respect to multiplication. And similarly, you see, if we consider the set of natural number with respect to plus, this is also not a group, because this is this set of natural number will not contain the identity element, even inverse also with respect to addition. Because if we consider suppose 3 is in n or not, yes, but the inverse of 3 with respect to addition is -3, and -3 is not in n. That means the set of natural number is closed, no problem, it is associative, but it has no identity element. Its set of natural number is not satisfy the existence of inverse property. Yes, that means this set of natural number is not a group. So my dear student, what you see here, if we consider a non-empty set, suppose Z, and if it is satisfies this closure property, then we call this is group wide. Okay, if it is satisfy the closure property, then we call this is group wide. And together, if we consider if it is satisfy these two properties, closure properties as well as associative property, then the structure or then the set non-empty set G is called semigroup, right? And also you see, the structure is satisfied these three properties, that means closure, associative and existence of identity. If it is satisfied these three properties, then we call this is nothing, this is monoid, right? And finally what we see, if it is satisfy all the properties, all the four properties, then this structure is called here group, right? My dear students, then the structure is called a group. So in the next class I will try to discuss some numerical problems which will be related to this structure. Okay, if you have any doubt on this lecture, then kindly drop a comment on Dropbox, then I will try to explain that doubt on the next class. Okay, bye bye, thank you.